Welcome back to mechanics and control of robotic manipulator. So far what we have covered, we have actually like talk about kinematics, dynamics, and we have seen like what is forward dynamics, what is inverse dynamics. Before that we have seen what is actually like a geometric model, how to find a forward dynamic, like forward kinematic model and forward differential kinematic model and all. We have actually like tried to see. And what I said actually like this particular course itself is actually like two subsection. So one is actually like mechanics, the other one is control. So this particular, you can say lecture, we are trying to cover what is, you can say control of robotic manipulator. So in the sense, we will first introduce the robot motion control, then we will actually like go how to actually like control the robotic manipulator. In that sense, you can actually like see what I usually give the same kind of disclaimer. And this particular lecture, what we are trying to cover, we are trying to give a basic introduction about what is, you can say, robot motion control, what are the trends and how actually like you can go again with robot motion control. In that sense, what are the types and what are the concerns related to that. So if that is the case, what one can see, like we will actually like start understanding more close to the, you can say, real system, which nothing but the closed loop for a definite task. So if that is the case, what we are actually like trying to see, what is motion control. So although we are going to classify robot control in several sections, so first we will talk about motion control. So what is motion control? Then immediately some people say it is automation, but not all the time automation is actually like not robot motion control. For example, some activity simply automated. Very simple example, you can take a chart, you can say chatbot. So which is actually like in one of the simple example, you take a online banking. When you open, you can see in one of the corner, it says that how can I help you? Then you click it, you will actually get sequence of question and then you will redirect into that case. So in the sense, what the several of operations are actually like automated. But here the robot motion control, in the sense, it is a field of automation, but what really actually like trying to see the moving parts, whatever you call the machines, in a controlled manner. So that is what we call actually like robot motion control, generally motion control. So we will actually like see in that sense what it is. So it is a open to closed loop. So far what you have seen, the inverse dynamics is actually like open loop, but right now it is actually like closed loop. That is what you call motion control. Then what it actually like monitor, it monitor actual desired path and corrects the position or velocity of the system. In the sense errors, it correct and try to follow the actual path. So if that is the case, what one can actually like expert in motion controller, the motion controller will give the motion profile. That is what we are trying to see as a trajectory generation. So some cases, for example, you have a robot point, manipulator point here, the end effector point, it's supposed to go here. For example, this is a 2 hour serial manipulator, it's supposed to go from this point to this point. So then what you need to do, you need to actually like say this is the target and this is the given point, how one to go there. So in the sense, what you are trying to do, you are trying to control the motor or actuator in order to actually like follow the point to point motion. So in that sense, you may actually like create several of, you can say, sub trajectory. It can follow like this, or it can go and reach here, or it can go reach here, like that, several aspects, right? So in that sense, you have to actually like see what to be done. So in that sense, what one can actually like expect, so you can actually like see that. So we are actually like trying to see a small aspect here. So what that mean actually, like we are actually like trying to see, so what really robot. So I already said robot would be having a body and as well as what you call the brain, right? So that is what we are seeing. So in the sense, you can see that the mechanical architecture what you have designed, that is nothing but a body. So in the other way around, the once you choose some particular configuration or architecture, definitely you have to find out the optimal design parameter that you can obtain from the system dynamics and given the specification. But even you do this optimization, do you think that the desired thing is fulfilled? No. Why it is so? Because the robot is not only a mechanical architecture, it is actually like also like consists of a brain, which we call a controller. So now the overall performance is actually like impact based on what you call, so, or influence based on the controller choice. So in that sense, even you have a very optimal mechanical architecture, but your controller is actually like poor in, you can say, performance, then the overall performance will go out. So that is what we are trying to say. So if that is the case, what one supposed to see, so we have tried to derive the dynamic model and all, right? So in that sense, what one can see, this is very similar to engineering application, where it is actually like impossible or very difficult to find out the exact dynamic model. So in the sense what one's supposed to see, so there are several unmodeled dynamics which are actually like there, because the exact dynamic model is actually like not possible due to so many reasons, which are we are putting as an unavoidable reason. For example, you want to actually like design the friction model. The exact friction model is not exactly described, right? So in that sense, what one's supposed to see, so how we can actually like put your exact controller. Further run, or moreover, what one can see, the robotic manipulator working in a real-time environment. In that sense, the external disturbance is one of the key factor which is inevitable. And in addition to that, you are thinking about real time. So there are several model which are actually like unmodeled in your case, several real thing you have not unmodeled. Further, even whatever you have chosen the parameter may be having a, you can say, variation. In that sense, what you can see that the uncertainty and external disturbance are inevitable. So then what we expect actually like some kind of advanced controller need to be there. So what is advanced controller, that we will discuss. So before discussing here, so we will actually like talk about something. So what that actually like, you can see like lots of theoretical, you can say, papers are coming into a, you can say, society. For example, even you Google it today, so you can see like at least one or two paper you can find in the recent past, in a week of time or in a month of time. So then why we are actually like thinking so much on the robot motion control? There is a big gap, not a small gap. There is a big gap between theory and practice. For example, now I propose one of the modern reinforcement learning based control, but that is not immediately going to come in a practice. So in the sense what one have to see, so there is a definitely a definite gap between the theory and practice. That is what we are trying to address in this particular short session. Okay. So in that sense, what one can see, so we can think about how the trends have come. Although I probably given in a lighter way, so I'm just you can say iterating here. So what that mean, in mid 70 the robots start coming. So those days what we like our forefathers have done, it is actually like classical side. Why it is classical? This is the beginning. So there we are actually like we have think about the mechanized machines. So in the sense, it is not really as a machine, it is a mechanized machine. In that sense, it's a simple pre-programmed motion. So if it is a pre-programmed motion, what we have to see, we have to think about exact model, no sensing is required. Whereas the scenario keep going, and several of, you can say, month or several years later, the same robot may not be fulfilling the exact model. For example, now I assume that this is actually like actually two body and it is connected. Over a period, what happened? There would be a wear and tear. This manipulator may actually like have look like this. So then your exact model would be actually like invalid, right? So then what people thought about it, can we use a feedback base? So then what people thought about, that is a reactive paradigm, where it is actually purely based on the sensing, and then actually like people ignore the model. So this also like worked in certain cases, where example you talk about only a small simplified manipulator, that to an actuator level, this was working good. But when you think about a system level, this was not working well. So then people try to combine this. So what they said, on the system level as a manipulator level, they go for a actually like what you call the classical side, where the individual actuator side, they use the what you call reactive paradigm. So that is what we are actually like going to call as a hybrid system. So this was actually like popular. Even now people are using this hybrid system. But what exactly here? The model based on higher level, but motion based in the lower level. Motion based in the sense we are actually like taking a feedback and react based on that. But what you can see, like these all actually like suitable in most of the manipulator theory which are we are focusing. But if you think about a general robot, so these are not risk, you can say, enough. For example, you talk about mobile robot, this is not really going to work. Then people think about something like a you call probability theory, where we can actually like seamlessly integrate both, you can say, inaccurate model and as well as you can say limited sensing capability. So then what they brought the probabilistic robotics, where actually like the computer is one of the important aspect, where mid 90 itself the computers have actually like come up with very well established. Then people are actually like seamlessly integrate both model and sensing. And then in that sense, what we are trying to use inaccurate model and limited sensing can be used and do it. In some other cases, what people thought about, why can't we use knowledge base? In the sense, you have several you call experimentation. Can we use those experimentation as a knowledge and then we can do it? So this was very popular in you call Eastern countries. We call neural network is one of the case, but the neural network is further improvised based on the data driven. We call learning based. So where the deep learning and reinforcement learning came in mid, you can say 2010s. So then 2000 you call 10 onwards. So we are actually using learning base in specifically the 2015 onwards. Everywhere we are bothering about learning based control. So now these are the general aspect. Now we go further. What we can actually look at it. So when you talk about robot motion control, what really you will look at it. So what you really look at it, so you will first understand the system, right? So first you familiarize the system, whether it is actually like touching the, you can say end, or it is actually like simply motion following. All those aspects you have to first familiarize the working nature. Later on, you will see what is the desired, how to achieve it. So in the sense, first premost task is actually like what? So the control design would be having several steps. First you familiarize, you model that, and then you incorporate the desired specification. So when you are talking about the control specification, there are several objective will come. So in fact, I explained already, the premost objective is actually like what you have to see, the system supposed to be stable. So in the sense, the stability is the one of the aspect, so that you need to bother. Then you have to actually like give one point to another point, whether you are doing it, which is we call regulation. Then you go for trajectory, which is nothing but a, you call, you can say time based, you can say path. Then you optimize what you call your overall control activity. In that sense, you see that the prime most is actually like stability is the important aspect. So if that is the case, what one can see, or what one can actually like classify the robot motion control into several forms. So one of the broad classification based on the trends. So one is actually like model free, which is basically reaction or you call motion based. So the other one is what you call model based. So in the sense, what one can actually like see, you can actually like make it the controller is model free control, purely depend on the feedback, and you can actually like make it as everything reaction based. So this is very easy, but the problem is it is a sluggish response and poor tracking performance. So in that sense, what people thought about it, they thought about the model based, so which is comparatively efficient and simple. But what the problem is actually, you should have an accurate model available to you. So if these are the cases, what people thought about it, can we ignore these things? So there are several implicit assumptions. One big assumption is model supposed to be accurately known, or in the other way around, the constant physical parameter are supposed to be accurately known. So these are not possible all the time. Then what people thought about it, they brought some kind of you call additional aspect. So they said that this can be achieved in two of the approaches. One is you can be a robust enough. So for example, you just ignore the effect of the external factor. For example, somebody is actually keep on actually like you can say bugging you. You just ignore him. What you can say, you are robust enough, right? So that is what. So you ignore the external influence, or you can say variation in error, the small variation in error. You ignore, then that is called robust control. So the other way around, you are actually like seeing the bugging guy and you are reacting and try to correct it. So this is nothing but what? So according to the situation, you are adapting. So there is a control called adaptive control. So now the robust and adaptive are two other cases. We'll discuss these two in very detail with a very simple example. But before that, you can just imagine what robust all about. You imagine you have actually like square base, you can say lunchbox, and the other one is hemisphere shape in lunchbox. You imagine you are actually like trying to wash, which is easiest. So definitely you can think about the hemisphere shape, right? Why it is so? Because there is no corner where the, you can say food particle would be, you can say dissipate, or you can say contaminate, or you call, you can say precipitate. So that is not going to happen in the hemisphere. So that's what we call robust design. Now the design is actually, you can say least affect with the external factor. So similar way you think about in control. So what least affect, in the sense, you see your variation of your error probably in the order of millimeter, but you are actually trying to correct even if it is actually like centimeter level. For example, you need to have a, you can say control input supposed to be 10 Newton, but instead of that, you are actually trying to correct with 100 Newton. What you are doing it, you are trying to do overwhelming. So this overwhelming is one of the fact which is actually like difficult, which is happening in robust control. That's why robust control is, although it is popular in robotics, but it is not applied in real time because it is consumed the lots of actuator energy. So in the sense what we have discussed is actually like two general approach which will overcome the implicit assumption which we have taken. So one is what you call robust. So where model is inaccurately available and as well as small error can be go away with the robustness. So the other one is actually like what you call adaptive. So what that means, it is actually like adapt based on the uncertainty and external disturbances. Okay. So now further classification we will discuss later. Right now you can actually like see how this can go. For example, you talk about in terms of dynamic model, you can control the overall system in kinematic level itself, where the first order system you can consider. So then it is called kinematic control, but manipulator control usually will not go with the kinematic side. But if your manipulator is a planner and you can say inertia is actually like ignorable or inertial effect is ignorable, then you can definitely go with the kinematic control. Whereas in the mobile robot, the kinematic control is very popular. So that is what we are actually trying to see. So now what we can actually like see, so the other aspect of, you can say, classification based on control. So one is what you call dynamic control. The other one is combining of these two. So we'll see these all in detail in upcoming lecture. Right now I'm trying to focus little more. So this is what's supposed to be as the first slide. So you know the robot manipulator can be used for several applications. One is just following. For example, I am saying that so you have a laser cutter. So this laser cutter is actually like supposed to follow some profile. So in the sense this is actually like laser beam which is coming. So in the sense you see that it is not really touching the what you call the workpiece. So it is just following. In the sense it is a free flowing of the, you can say, motion of the end effector, which is the laser beam, you can say, generator. But some cases, you imagine, so now this is actually like a pen. Okay, this pen is actually like touching on the paper and drawing similar. So now what you need to see the touching supposed to be appropriate, then only you can draw. So now you have to see the force control, right? On top of that, this is supposed to follow in a line or some curve. So then what you have to see, you have to have force and position control. But what one supposed to see here, there is one limitation. So the actuator set is only one. The same actuator is supposed to provide the force or position. So in the sense you have to use the switching. So further run, this can be actually like make it as a, you can say, slave, and I'm actually like coming with a master similar to this as a small joystick kind. So then what we can do it, we can actually like move this and the main manipulator can move further. So what we call that particular control called impedance or haptic control. The impedance is a very general name. So this is what the further classification based on the interest or application. Then what are the other classification we can discuss here? So one of the other classification we can discuss based on what you can say working space you are going to consider for the control. Whether you are considering everything in operational space, then we call task space control, or everything you are considering in a configuration space, then you can call a joint space control, or you are actually like considering everything with a sensor. So you have a sensor space. For example, you have camera, you have encoder. So you are actually like using everything based on the sensor value itself. Then it is called sensory task space, or some people simply call sensor space control. So we would be focusing these all three. In specific, we'll see the joint space control in detail. The same control technique can be applied, a small modification we can do that can be considered as a task space or sensor space. So in that sense, what we are actually trying to see in the other end, we are trying to see other end we are trying to see the other end is actually like how that motion control come into picture, because in the beginning we are focusing on the motion. So the motion control further classify based on the nature of reference input. So the nature of reference input is actually like time independent. So in the sense it's all constant. So then what you can say, for example, you take the air conditioner. So you say 20 or 22. What you are trying to do, you are setting the point. So 20 or 22. You are trying to actually like control based on the given thing. So for example, now you have the point here and you are trying to go here. It is just a point. You are not defining. For example, you take a parking, the car parking. So you are not actually defining at what time you have to actually like fulfill this task. Some of the expert driver will take few seconds. Some of the learning driver will do back and forth, the reverse and forward. They take a further time, right? The sense the set point control is time independent. Whereas if the trajectory or the given input is actually like based on the time, in the sense it is dependent on time, then that kind of controller what you call tracking, because it is tracking the profile. So the tracking control sometime we call servo control, the set point control sometime we call regulation control. So these are based on the reference input. But I already told we have some concern, right? So what are the concern that we can actually like discuss? So one of the concern is actually like what you can actually like see. So you might have actually like come up. Probably most of you are mechanical, but some of you might be electrical or electronics. You would have seen that whenever you talk about motor control, the immediate thought process will come that you have to refer to a PI control. So why it is popular in PA? Because the actuator is actually like mostly we define in what you call in a first order. Even if it is a second order, the control or you can say the DC motor is stable, because the second order differential equation in that case all the coefficients are actually like positive. The open loop system itself stable. Then you can actually like apply P and I where the steady state error would be converged to zero. Whereas in a robotic system, it is not so popular. Why? Because the robotic system, if you consider, even you take a first order, you can say not first order, the first simplest model we have seen in a dynamic system, where we have taken a simple pendulum as a 1D of rotary manipulator. That model you recall, so ml squared theta double dot minus mgl cos theta or sin theta, right? In the sense what one can see, the system model where one of the coefficient is missing, in the sense the theta dot coefficient is missing. Even you incorporate theta dot, so mostly the open loop system is actually like what? It is unstable or marginally stable system. So in the sense, the PI control further it is deteriorate because you are adding one pole in a closed loop system at zero location or very close to zero. In the sense, what you can see, the system can go immediately unstable. So that's why what we are trying to use as a PD control. So the PD control is actually like the first preferred control in robotics, because the PD control will give a damping, and the system, if you make it as a closed loop, the closed loop system is stable. Okay. The PD control, in the sense what you are trying to do, you are trying to make one, you can say, pole in the left of the plane. So in that sense, what you are trying to do, you are actually like trying to do very, very simple aspect as a closed loop system. So that's why even now you can see that the PD control is the immediate choice for the robotic manipulator industry. And even you want to actually like the PD controller will have a steady state error. You want to take away the steady state error, people go with PID. So these are the immediate choice. But what one can actually see the other side. So what the other side? So people thought about the inverse differential kinematics or inverse dynamics are actually like controlling, right? So that is what I mentioned. But this controlling is an open loop, or some people call it is feed forward. So, but when you are thinking about the motion control or position control, it should be feedback control. So that is what we are trying to address in the next lecture, upcoming lectures. And with that, you can actually like see the real, you can say, picture of the overall manipulator, where you started from the conceptual design to the final closed loop. And once these all done, you do the detailed dynamic simulation along with the closed loop. And then what one can actually like see, you can actually like do, see, you can say investigation analysis, then you can redesign your overall manipulator, and then you can give it for a fabrication and testing. Okay. So with that, I'm actually like ending this particular short lecture, and we will see upcoming lecture with the kinematic control and dynamic control, several further schemes what we discussed earlier, like what you call robust, adaptive, all those things we will see in upcoming lectures. Right now, I'm closing this particular lecture here with the introduction on robot motion control. Okay, thank you, and see you then in the live session. Bye.